Hello everyone. Let's get started on our second lecture here, Geometry Chapter 7 Part 2. We're going to be going over parallel lines, similar triangles, transformations, and scale drawings and models. So today, starting with parallel lines and proportions, we're taking a look at within triangles. If we have a parallel line, similar to our figure over here, then we're going to say that in any triangle, a line parallel to one side of a triangle separates the other two sides proportionally. This is the triangle proportionality theorem. The converse is also true. So this is in your book as two separate theorems, but we're going over them together here. And basically we look here saying that if we take the section line segment here, xy, and set it parallel to rs, so here we have xy, if it is parallel to rs, then this segment, Rx, over xt, looking at our proportion here, is equal to Sy over Yt. And alternatively, if we look at it from the other direction, Rx over xt is equal to Sy over Yt, then xy and rs are parallel. So basically, they have this line here that's just separating these two portions of the sides of our triangle so that we can say that they're proportional to each other. And if we have it noted that they're proportional to each other, then we can say that these two lines, x, y, and rs, are parallel to each other. Also in this we have if x and y are the midpoints of r and t, here's rt, x, and of st, here's y, they're saying if these are the midpoints, then xy is what's called a midsegment of the triangle. The triangle midsegment theorem states that a midsegment is parallel to the third side and is half the length of that third side. So that's represented here. If xy is a midsegment, then xy is parallel to rs, and xy equals 1/2 of rs. All right, so here we have a couple of examples where we're looking at this and attempting to solve for x. So starting off here, we can see that we have AE set at 18, EC at 6. Over here, we have AF as x22 and FB as x plus 2. So we start with, since EF, and EF over here is this line right there, is parallel to CB, okay, we see the notations for parallel, then we can say that AF over FB, so these two sections of the triangle here, AF, FB, equal AE over EC. We're still dealing with proportions, so we were dealing with proportions in our last lecture. We're still dealing with these types of proportions. Remember, a ratio is just setting it up as a fraction here. A proportion is once we're comparing the two with an equal sign in between. So two ratios compared with an equal sign is a proportion. So let's go ahead and fill in those numbers now of AF, FB, AE, and EC. Well, AF, we have x plus 22. FB, we have x plus 2. AE, we have 18. And EC, we have 6. Then all we do is we cross multiply right here, getting all of that in one line there. Then we simplify it together, we get our like terms together, and then we solve for x. And the answer we get is x equals 8. And if you put that back into the problem, you can check it out to make sure that you've gotten the right answer. On our second example here, we're taking in triangle GHJ, HK equals 5 and KG equals 10, and JL is 1/2 the length of LG. Is HK parallel to KL? Well, HJ is over here, and we're saying that, asking if this is parallel to KL. So what we're told is that HK is 5, KG is 10, and JL is 1/2 the length of LG. So we have over here 10 for this longer segment, half of that over here, 5. So if we say that this is 1/2 of this segment, can we say that these lines are parallel to each other? Well, using the converse theory of triangle proportionality theorem, was to show that HK over KG equals JL over LG. Let JL equal X and LG equal 2X. See, they asked us with the half here, so 2X meaning twice as much, so we're going to set it then as HK equals 5, KG equals 10. We get the ratio, the scale here, of 1/2 when we simplify that. So then, if we have JL equaling X, LG equaling 2X, that can also be simplified just as 1/2, because it's 1X over 2X, which is just the same as 1/2. Since 1/2 equals 1/2, the sides are proportional, and our two lines in question are parallel to each other. Okay, so let's move forward. Let's take a moment here to practice these problems. Go ahead and pause, copy down the information that you need onto your own sheet of paper. For each of these practice sections, make sure that you get them on your own sheet of paper, take pictures of each, and then email them to me after you're done so that I can give you a grade for the work that you've done in our class today. So take in mind that you are doing the same thing. You're just getting these set up and you're solving for x, just as we did in our example just before. If you need to go back and review the example, go back and review it, but make sure to pause here so that you can copy down the information that you need. Pause until you're done with each of these problems.
Do you still want to look for him?
Is that the castle beyond the Goblin City?
Turn back, Sarah. Turn back before it's too late.
I can't. Don't you understand that I can't?
What a pity.
It doesn't look that far.
It's further than you think. Time is short. You have 13 hours in which to solve the labyrinth before your baby brother becomes one of us forever. Such a pity.
And by the way, if you have not watched the movie The Labyrinth, you totally should, because it's awesome. But let's go ahead and take a look at those answers now. So here is the answers page. Feel free to pause here again so that you can write down your answers, check all of your work. Remember that what you send to me, I'm going to be looking for the actual work and not just the answer, so you can't just copy this down. Even if you did speed ahead past our little pause points there, if you just write the answer down, you're not going to get credit for it. So, just like with over here, we had set them to our proportions and then solve for x. Number 1, x equals 7, and you do the same for each of these. If you have any questions, if you have any trouble with any of the homework that we're doing, the classwork, then go ahead and mark it down. Email me, text me, call me, whatever you need to do so that we can discuss each of the problems that you have trouble with. All right, let's move forward. All right, now we're dealing a bit more specifically with parallel lines here. And we've done parallel lines before, we've done transversals before. So this is more of the same, but with a few more rules added in. When 3 or more parallel lines cut 2 transversals, they separate the transversals into proportional parts. If the ratio of the parts is 1, then the parallel lines separate the transversals into congruent parts. All right, all that means there is we're dealing with ratios, and sometimes a ratio will be 2 to 1, 3 to 1. So that's an increasing ratio where it's getting bigger. If we have a ratio where it's 1/2, 1/3, then it's decreasing, and we'll see how that affects figures a little bit later. But if the ratio just ends up being 1, then they're actually congruent. They're the same measurement. So whatever our ratio is, that's how our problems are going to be affected here. So if we look at our figures over here, it's asking you to look at the different lines, line 1, 2, and 3, and see that they're parallel to each other here. And if you set up the proportion again, A over B equals C over D, then we have our proportion to be able to solve for the measurements of each of these here. Over on this side, it says if line 4, 5, and 6 are parallel to each other, and we see that they are here, then U over V equals 1. Why is that? Well, because we actually have them as congruent right here. So then W over X also equals 1. So they're going to be congruent there so long as they equal out to 1. So the example here says refer to lines 1, 2, and 3 above. If A equals 3 and B equals 8 and C equals 5, then you need to find D. So they set that up right here. 3 over 8 equals 5 over D. Then, once again, they cross multiply so that you get 3 times D and 8 times 5, end up with 3D equals 40. Then when you solve for D, you end up with D equaling 13 and 1/3. So let's take a look at some more practice problems in how to do this. Go ahead and pause here on this page. Notice with a couple of these, as if you're having any trouble, that this one especially might give you a little bit of trouble, but notice the congruent marks here are indicating that there's going to be congruence between each of these. So it's actually much simpler than it looks, because if they're congruent and they've given you a full number right here, well then these have got to be congruent, right? I think I've already given away the answer, but go ahead and work through all these problems, pause it here, and put that on your worksheet as well. Hey, make sure you get that done. Don't go to the answers too quickly. Okay, here are the answers. Again, check all your work. Make sure that you've got your work actually written down. I want to see those proportions. I want to see it written out clearly and not just the answers on the screen. So if you have any trouble, again, go ahead and mark it out and ask me any questions that you have about it. Next segment here, we have special segments and similar triangles. When the two triangles are similar, corresponding altitudes and angled bisectors and medians are proportional to the corresponding sides. So we're taking those parts of a triangle that we've examined before, the altitudes, the angled bisectors, and the medians. We're talking about the proportionality of them within similar triangles. Remember, similar triangles are triangles that are not necessarily the same size, but they have a proportionality to them. There's a scale that shows them being similar. So since triangle ABC is similar to triangle XYZ, the measures of the angled bisectors are proportional to the measures of a pair of corresponding sides. So we have AB over XY. So AB, this is our first triangle here, and that side corresponds with the side XY. So they set them up as a ratio here. Then filling out the proportion with the second ratio, we have BD right here over WY. So we have our different angle bisectors here shown and marked out. Now when we fill in the actual numbers that we're given, we have 24 over X, because that's the side we're looking for, and 10 for BD over 8 for WY here. So once we've got that, once again, it's the same process, the same step. We're really just doing the same things over and over again, but it's with different sections and different parts of the triangles, different parts of the figures that we're looking at. So keep in mind, again, we're just going to cross multiply here so that we get x times 10. 10x equals 24 times 8. 10x equals 192, or x equals 19.2. Okay, here are your next practice problems to look for. Go ahead and solve for x. Notice that we have similar triangles on each one here. They're easily marked out which angles are congruent, which sides are congruent to which sides, and we can tell the proportionality of each of these here. So go ahead and pause and take a few minutes to get this done, please. Again, make sure you don't speed through it too quickly. Make sure you get your answers written down correctly and get to the answer page at the right time. All right. Now that you've gotten the answers here, go ahead and get those down again. Check all of your answers. Get back to me with any questions that you have. The next section is that we're dealing with more parts of similar triangles. And we've got our triangle angle bisector theorem. An angle bisector in a triangle separates the opposite sides into two segments that are proportional to the lengths of the other two sides. So here we've got our angle bisector theorem. Angle bisector right there, the theorem goes that since SU, that's our angle bisector, is an angle bisector, then RU over TU equals RS over TS. So that's our proportion right there. Once we fill in all of the pertinent information that we've got, then we cross multiply, solve for x. Once again, x equals 10 in this scenario here. So that's our example. Let's move forward to the practice problems. Again, if you need to come back to look at the example, mostly to look at how this is set up so that you can actually see which section goes into which ratio and things like that. Because I think by now you should probably be getting used to how to do this cross multiplication here. So we've got our new problems here solving for x, just like with all the others. We've got to set up our proportions properly so that we can then be able to cross multiply and find the right answers. Go ahead and pause and work on these. Okay, here we go with the correct answers for each one. If you got something different, work through it again. If you can't find the right answer, again, just contact me. We'll work through it together. Next, we've got similarity transformations. Identity similarity transformations. We've dealt with transformations before. Remember, that's just moving the figure into a different position. We have reflections, we have dilations, we have all sorts of ways that we move it. Today we're going to be dealing mostly with dilations, but we have something that we're dealing with that is a kind of either an enlargement or a reduction of the figure, so that when it's redrawn, it's either going to be bigger or it's going to be smaller. And that's going to be the ratio by which it gets bigger or smaller, and they label it as K here, the ratio of a length of an image to a corresponding length of the pre-image. A dilation with K greater than 1 is an enlargement, and a dilation with 0 less than K less than 1 is a reduction. Basically saying anything that is a fraction, if you come up with a scale of 1/2, then you're actually making the figure smaller than what it started out with. If you have a scale of 1, then you're just copying the figure in the exact same proportions. And if it's greater than 1, 3/1, something like that, then you're actually increasing the size of the second drawing of the figure. So take a look at a couple of examples of that here. We have an original square, which then gets enlarged out here into a larger square. With a triangle over here with coordinates, we're doing the same thing, and you could look at either one of these as starting as the smaller one and then moving out to the bigger one, or starting as the bigger one and reducing down to the smaller one. With the triangle specifically, the scale factor is 2. Well, how did they get the scale factor of 2? Well, it's really simple once you have the coordinates here. What you're going to be doing is you're actually going to just be placing the coordinates with the opposing coordinates here from the original figure. So if we look here, we have a 6, we have a 3, we have a 4, we have a 2. Well, what is that? What ends up happening? If we put 6 over 3, then we've actually got 2 over 1. If we put 4 over 2, then we've actually got 2 over 1 again. So the scale of this vertices increased by 2 to get over here. And that's true for each of these vertices. We went from 1 to 2, so it actually multiplied by 2 to get over here. And 3 multiplied by 2 is 6. 1 multiplied by 2 is 2. So the scale is 2. It increased by 2, not by adding 2, but by a factor of 2 each time to get to these points. We'll see a couple of problems dealing with that in just a little bit. So the steps for finding that scale factor is to identify a pair of similar sides. So let's say that we've got these sides here. We use the coordinates to create a ratio in the form of a fraction. So right here, let's say that we've got 4 over 2. Well, that equals 2. We've got 6 over 3. Well, that equals 2. We've got 2 over 1. Well, that equals 2. 2 over 1, also 2 again. So likewise and so forth, we end up with the scale of 2. And you check that out. You make sure that it's true all the way around. If it's not, then we do not have similar figures. All right, let's move forward to a couple of, right here, we're looking at verifying similarity. I didn't want to put too many of these on here because the actual worksheets that I have are a little bit difficult to read the figures. If you look, you can see the lines here. The lines are a little bit harder to see on this figure. There were a lot of them like that, a lot of problems, and they ended up looking even a bit more difficult than these to see where it was. So I actually wanted to not give you too many of these, but it's important that you know that you can verify that a dilation produces a similar figure by comparing the ratios of all the corresponding sides. For triangles, you can also use the side angle side similarity. So the example here is to graph the original figure and its dilated image. Then verify that dilation is a similarity transformation. That's verifying that we actually do have similar figures here. So with the original, we're taking all the coordinates and we're graphing out the figure, and they graph out the figures here. So, and you graph those out, then you use the coordinate grid to find the lengths of the vertical segments. So AC here, you can just count the boxes, and that gives you the number for the length of AC. And you do that for AC, you can do that for the corresponding side over here on the similar figure DF. So you have AC over DF equals 8 over 4, or reduced down to 2. Then we look at AB over DE, do the same thing, comes down to 2. So since the length of the sides that include the angle A and angle D are proportional, then triangle ABC is similar to angle DEF by side angle side similarity. Notice how they compared this side to this side to this side, and then use the angle in between for side angle side. Now, on the second example here, we're seeing something a little bit different because over on this first example, we're able to use these straight lines, the vertical and horizontal here, to just count out the length, to just count out how long each side is. But if we don't have those lines just horizontal and vertical like that, but instead have diagonals, then what we have to resort to is the distance formula. So we use the distance formula with the coordinates in order to then come up with the distance for each side. It's our old friend, the distance formula. Don't be afraid of it. Don't be afraid to use it. As a side note, some of you may have noticed in the past, and some of you may be very excited to hear, that you can actually use the Pythagorean theorem instead of using distance formula if you want to. I would still recommend knowing distance formula and knowing how to do this, because this will definitely get you the right answer every time. Or I think some people may have trouble figuring out Pythagorean theorem to end up with the wrong answer. But let's assume that these diagonals are actually the hypotenuse of a right triangle. Notice that you can create vertical and horizontal lines out to the side right here. If you follow my cursor, you can count those out and create an imaginary triangle here with the side of our figure being the hypotenuse, and you can actually use Pythagorean theorem to find out the length of each of these sides on each figure. So that's another way that you can do it without having to use the distance formula, but don't knock the distance formula. It's very important to know how to do it. Once you have the length of those sides, you find and compare the ratios of the corresponding sides, and again, you find that it is a factor of 2, that it is 2 scaled each time. Okay, just a couple of practice problems here for how to do that. On your own sheet of paper, graph the original figure and its dilated image. So we've got our 3 points for an original triangle and 3 points for a dilated image of the second triangle for each of these. This one we've got a word problem. So pause here, find what you need to find, get it on your sheet of paper, work out the problems before moving on to the answers. All right, so the answers are here. It's not going to show you the graphs, but it's showing you that you can find out that this is similar by the side angle side, and this is similar by proportional sides. Then we've got the coordinates over here for each of those points written down for number 9. If you had any trouble, if you have any questions, once again, write it down, contact me. The next section that we're dealing with is actually the most pragmatic part of what we're doing with all of this scaling. It's not just figuring out different sizes, but one of the things that we use that for is the ability to make maps. We scale down our maps to a certain size so that you can actually look at a map and see that little key in the corner here that shows you that this measurement of 0.75 inches is approximately 6 miles. So that if you take a ruler and you put it on a map that has that key, you can actually figure out how many miles something is, what the distance is if you want to travel using a map like that. A lot of people are probably past this point now because you just type it into your phone, you find out through maps, through Google, like how far something is away from you. You don't need to actually do any of this. One thing that you need to keep in mind is there may come a day where your battery dies, where you're out somewhere camping, you don't have access to technology, but you might have a map. Actually, if you're traveling out somewhere where your phone is going to die, you should have a map. You should keep one with you. A physical map is an important thing if you're going to be out camping or doing anything of that sort. And you can figure out not only which direction you're going and which the best way to go is, but how long it will take you to get there, figuring out how far it is. Using a scale, like we've been doing, you can create an estimate of how far things are doing that. So we take a look here. It says, write and solve a proportion. Let x represent the distance between cities. So we have our proportion here. Our first ratio is inches over miles, 0.75 inches over 6 miles. That's our key over here. And then equal to, and we have the actual measurement of how far we're trying to measure, 1.25 inches. And we want to know how many miles that is. So we do our cross multiplication again, solve for x, and we get 10 miles. So our second method then says write and solve an equation. Let a equal actual distance and m equal map distance in inches. Write the scale as 6 miles over 0.75 inches, which is the same as 6 divided by 0.75, or 8 miles per inch. So a then equals 8 times m. The next step is m 1.25 times that 8, and then we solve and we get 10. So we come up with the same answer. The distance between Penham and Menlo Fields is 10 miles. It's two different ways to be able to do the same problem. Again, we've been doing a lot of this cross multiplication. This other step here is basically the same thing, but we're just taking the information pretty much backwards and putting it into the problem in order to solve it that way. All right, let's take a look at a couple of practice problems involving this here. Oh, no, sorry, we have one more example here on our scale factors. The scale factor of a drawing, or the scale model, is the scale written as unitless ratio in simplest form. Scale factors are always written so that the model length in the ratio comes first. So the example here is a dollhouse that is 15 inches tall is a scale model of a real house with a height of 20 feet. What is the scale of the model? So to find the scale, write a ratio of the model's length to an actual length. So we have model length over actual length. We fill that in with 15 inches over 20 feet, or the ratio of that is 3 inches to 4 feet. The scale of the model is 3 inches to 4 feet. So how many times as tall as the house is the model? Multiply the scale factor of the model by a conversion factor that relates inches to feet to obtain a unitless ratio. 3 inches over 4 feet equals 3 inches over 4 feet times 1 foot over 12 inches, which equals 3 over 48, or 1 over 16. The scale factor is 1 to the 16th, or 1 to 16. That is, the model is 1/16 as tall as the actual house is. So here are our practice problems here. Go ahead and pause, work through these problems before we get to the answers. Again, if you have any questions, email, write me, text me, whatever you need to do. We'll work through it. That's all the answers you need, right, guys? No, okay, here are the actual answers to those problems now. All right, so make sure to check your answers. And that's all for this lesson, folks. Make sure to check iGrade. Make sure we're on target here and getting things done. Make sure that you got the stuff that I posted on iGrade previously, the stuff that I will also post on iGrade today. All of that stuff from Monday and today is going to be due next week on Thursday. Again, that's through email. You're going to be emailing that to me. You're going to be taking photos of what you need to, scanning what you need to, getting whatever it is that you need. If you can find a way to do it electronically, you can do it that way. Just marking it there, but I do need to see your work on a lot of these problems. So it's going to be a lot of taking photos of the things that you have done and emailing it to me. Again, guys, if you have any suggestions, have any problems with how we're doing stuff now, let me know. We need to organize this in a way that is most beneficial for you. I really hope that you all are staying safe and staying healthy while we're all stuck at home. All right. Have a good day, guys.